All right, so the last thing we talked about was surface tension, okay? And what this was about was the following. Okay, so we saw that if you have a molecule in, so here's a, what this is here's a glass of water. So here's a molecule inside the glass, and so this molecule is attracting that molecule in that direction. This molecule is attracting this molecule in that direction. This molecule is attracting like that, and this is attracting this. So if a molecule is inside, the net force on it is 0. Okay. Now let's look at a molecule on the surface. A molecule on the surface, on the other hand, this guy is pulling him that way, this guy is pulling him that way, this guy is pulling him this way. There's no guy pulling him up in that direction. So there's a net force on him downwards. Okay. So for every molecule on the surface, there's a net force on him pulling him downward. Why isn't he going downward? Well, somebody's got to stay on the surface. There's no room. Okay. So to be on the surface, it's like, so to keep a molecule on the surface, so think of a spring. So we're going to model it like this. So here's a spring. Okay. To put that guy on the surface, you had to pull the spring and put him there. And this force that this guy is exerting is modeled by this spring. Okay. And if you stretch a spring, there's energy in the spring, because if you let go of the spring, that'll snap back. Okay. So to put a molecule on the surface, it costs you energy. You have to spend money to put a molecule on the surface. So in that glass of coffee, every molecule that's on the surface, it costs energy to put it there. So let's say you have a bunch of water. Okay. It costs you money to put a molecule on the surface. So what is it that you want to do? You want to spend the least amount of money. You want the least number of molecules on a surface. Did you guys understand that? So if you have a raindrop falling, if it's a small drop, it will be a spherical drop. Why is it spherical? Because for a given volume, the surface of a sphere has the least area. You won't find a raindrop falling like this, like a hot dog or something like that. Because for a given volume, that's more area. Did you guys understand that? Okay. So every molecule on the surface, it costs energy to put there. So the surface of a liquid surface is like a stretched rubber membrane. Okay? And that's the tension. Okay? That's called surface tension. Okay? Now, and that's what's supporting this bug. Okay? So when this bug is on the surface, so it's like this, and now I'm going to draw the bug like a point. Okay. So this tension in the surface, tension will denote by T, and here's the weight of the bug. Okay. So what is happening is there's the component of the tension, there's this component of the tension, that's canceling, and this component of these two components of the tension. This is the component of this tension, that's the component of that tension. These two guys are supporting the weight of the bug. Okay, greater the tension, heavier the bug you can support. Okay. So this guy can walk on water, and here you can see that this pin is being supported by the surface of water. Now, the attractive force between mercury molecules are stronger, so the surface tension would be greater. So if you had a glass of mercury, let's say, you could support a heavier bug. Okay. So we saw this last time, and that's surface tension. Okay. And we'll come to that. It'll play an important role. So surface tension is denoted by gamma. And here's how you measure surface tension for a fluid. So for instance, if you wanted to measure surface tension for soapy water. So you guys have seen devices like this to make soap bubbles and stuff like that. So here's a wire, and this wire can slide. By the way, I've changed the formula. If you printed notes, I've updated the file. Okay. So here is this soapy water film. Okay. And here's a sliding piece of wire. Okay. And let's say you pull on this guy, the force you apply. Now every film has two surfaces, so the length of the edge is 2L. L is this length. Okay. So surface tension is how much force you need divided by the length of the edge. Okay. So the greater the force you need, the greater the surface tension. Okay. So for instance, this is a film of soapy water, and you can measure the surface tension. And so if this was a mercury film, you would need a bigger force to pull that. Okay. And here's a list of surface tensions. Okay. So surface tension for water at various temperatures, surface tension for water, and the units are Newton per meter. It's 0.072. Okay. All right, we'll come to that. So we'll talk about breathing in a second. All right, so let's look at this. Okay, so what this formula is saying is the following. So let's say you have a balloon. Okay, so the balloon has a surface tension. It's under tension. Okay, so what this balloon does is it adds extra pressure inside to the air. Okay, so what this formula is telling you is if you have a bubble, okay, the bubble surface increases the air pressure in there. And it increases the air pressure by this much. 4 times the surface tension divided by the radius of the bubble. Okay, so what does this mean? The smaller the radius of the bubble, greater the increase in pressure. Okay? Smaller the radius of the bubble, greater the pressure. So the extra pressure inside a bubble is given by this. And this will be important for when we talk about breathing. Okay? So smaller the bubble, greater the pressure. Okay? So here's a little simulation. Okay? So here are 2 balloons that are connected. Okay? And so initially the air is not connected. Once we remove the connection, what do you think will happen? Okay. So let me try and get this. Why isn't this working? There you go. Okay, how do I reload this? Why wasn't that loading? All right, we won't worry about that. All right, so we have two balloons. One is the balloon material is the same, so gamma is the same, and we're going to blow this one up larger and this one smaller, and we're going to connect them. What do you think will happen? Will air move from here to there or there to here? Okay, so what will happen is the following. Remember, for a fluid to flow, it flows from higher pressure to lower pressure. Okay, so since this radius is smaller, the radius is smaller, the pressure is higher. So air will move from here to there. Okay. All right, so, and this balloon will go to zero. All its air will move from here to there. Okay, so that's what will happen. Okay. Now we'll talk about this in a second because this will be relevant. In emphysema patients, what happens is a bunch of alveoli combine and become bigger alveoli. Okay, so they become bigger like this, and when they're bigger, the pressure inside is smaller, and these patients have trouble breathing out. Okay, they have trouble expelling this air, so that's a problem. Okay, all right. So let's talk about that now. Before we do that, before we talk about how breathing works, we'll remember this formula, and let me solve this problem before we come back to it. Okay. So here's what we'll do is we'll calculate that extra pressure. The extra pressure is 4 gamma, the surface tension, divided by the radius of the bubble. Okay, R is the radius of the bubble. So calculate the pressure in millimeters of mercury. Okay, and again, I just want you to sort of have a feel for the answer. Inside a water bubble, the water bubble is, so when they say water bubble, what they're telling you is giving you the value of the surface tension. Okay. Again, you don't have to know all the details of the thing, just get a sense for the answer. Inside a water bubble, that's 2 times 10 to the minus 2 centimeters. It's 0.2 millimeters. That's the radius. 0.2 millimeters is about that tiny. Okay, and this is the size of your alveoli in your lungs. Okay. In radius. Then we'll calculate a water bubble 5 times larger. Okay, 5 times larger. This is 1 millimeters. Okay, 5 times larger. That's the size of alveoli in an emphysema patient. Okay, so what has happened is, do you guys know what is the volume of this sphere? 4 pi by 3 r cubed. Okay, so the radius is 5 times. So in an emphysema patient, about 100 alveoli will have combined and become 1 alveoli. Okay, so that's what's going on there. Okay, so water bubble 5 times larger, and then a bubble of water 2 times 10 to the minus 2, so the same radius with a surfactant. What a surfactant does is it reduces this number. Okay, and we'll come to that. So in your alveoli, it's not just water, it's a surfactant. There's proteins in your alveoli that reduce this to half the value of water. Okay, and we'll come to that. Okay, and it reduces the surface tension to 0.037 Newton per meter. Okay, so here's the calculation for the first one. This is 0.2 millimeters. This is water, and the pressure is 10.811 millimeters of mercury. So this goes through that calculation. So this calculation, this pressure calculation, which we got that answer, is for this radius and that surface tension. Okay. So there's the surface tension of water, and there is the radius, there's the pressure in Newton per meter square, and that is converted to millimeters of mercury. That's what this calculation is about. All right, so here's all I want you to remember. Okay, this is the normal size of an alveoli. This is millimeters. This is the normal size of an alveoli, and if the surface tension was that of water, the excess pressure would be 10 millimeters of mercury, 11 millimeters of mercury. If the alveoli size was 1 millimeter, 5 times greater, the surface tension was the same, the pressure has dropped to 2 millimeters of mercury. Okay, you need high pressure to expel air from your lungs. In an emphysema patient, when the alveoli become bigger, when they coalesce and become bigger, now they have trouble breathing out. We'll come to that in a second. Okay, so that's what this problem is about. The last part is, again, you have normal size alveoli. We've reduced the surface tension by adding surfactants, okay? And the pressure is that, okay? Now, when the pressure is too high, so for instance, sometimes it happens in newborn kids, they have trouble breathing because it's like if you have a balloon, have you guys used balloons where it's hard to blow them up because the rubber is too stiff? Okay, so kids, some newborn kids have that. This number is too high. This number is too large, and they can't blow up their alveoli, so they have trouble breathing. Okay. All right, so now let's figure out how breathing works. Okay. So I'm going to draw a simple diagram. So here's, okay. And again, for a fluid to flow in any direction, you have, so for air to flow, if you want air to flow this way, what you need is high pressure here and low pressure there. Air will flow from a higher pressure region to a lower pressure region. Okay. So now let's make sure that, so here's a single alveoli. Oops. Yeah. Don't laugh at my drawing. That's minus 10 points if you laugh at my drawing. You're laughing. Yeah. All right. What is the pressure out here? 1 atmosphere. Does that change? It does not change. Okay, so if you want air to move in here, what you have to do is you have to reduce the pressure to less than 1 atmosphere there. So when you want to breathe in, you have to reduce the pressure inside the alveoli. This pressure is not changing. When you breathe out, you have to increase the pressure more than 1 atmosphere, right? Okay, so what you're doing is the outside pressure is not changing. So to breathe in and out, you have to change the pressure inside your lungs, inside your alveoli. Okay. Now in this business, so here's the actual pressure. What they quote is the gauge pressure, which is the actual pressure minus atmospheric pressure. So what is the pressure here? The actual pressure is 1 atmosphere. 1 atmosphere minus 1 atmosphere is 0 millimeters of mercury. Okay, that's just the number. Okay, so let's say when you're not breathing, when air is not moving in or out, this is inside the alveoli, it's 0 millimeters of mercury. Okay. All right, but this fellow, P equal to 4 gamma R, because this is like a rubber balloon, this increases pressure, and under normal conditions, the pressure is 5 millimeters of mercury. You guys understanding this? So this pressure is 5 millimeters of mercury. Well, if this was 5 millimeters of mercury, this pressure is higher, that air should go out and this alveoli should collapse. Well, how do you prevent that? Okay, so here's what you do. So when you breathe in, what do? You lower your diaphragm, okay? And inside your thoracic cavity, what you do is you maintain a negative pressure. See, here's the intrathoracic cavity, and this is from chapter 7. You learned this. You are maintaining a negative pressure. Negative pressure meaning it's lower than atmospheric pressure. So inside your thoracic cavity, there's a partial vacuum. So, and that ranges from -4 to -8 millimeters, okay? So, if, so there's the normal circumstance, and if you maintain -5 millimeters of mercury, then -5 and +5, it's 0, and now air is not going in or out, okay? Now let's say you want to breathe in. What do? You lower your diaphragm. This pressure goes to -8 millimeters of mercury. And -8 plus 5 is -3. Now this pressure is lower and air will move in. Did you guys understand that? Okay. When you want to breathe out, what do you have to do? You have to increase the pressure. You raise the diaphragm. This pressure in the thoracic cavity goes to -4 millimeters. So this was really 5.5, okay? So 5.5 minus 4 is plus 1.5, and this 1.5 pressure will drive the air out. Okay, so when you're breathing in and out, what you're doing is you're expanding and contracting this thoracic cavity. Okay, and that's how you're changing the pressure inside here, and bringing in air or expelling air. All right, so let's look at the emphysema patients. Okay, which are the emphysema patients? These guys are the emphysema patient. Their alveoli has become big. Okay? And are you guys understanding this? Are you following this? Okay. So here's the emphysema patient. Their alveoli has become big. Okay. So for the emphysema patient, that's 2 millimeters of mercury. Okay, remember the thoracic cavity, the capacity is only to go from -4 to -8 millimeters. Okay. All right. So for the emphysema patient, even when you're trying to breathe out, you brought your diaphragm up. This has become -4 millimeters. -4 plus 2 is -2. You can't breathe out. Okay, so even if because your alveoli got bigger, that pressure decreased to that, you have trouble breathing out. Okay. All right, so let's look at the other case. So sometimes surface tension in the alveoli can be too large, making them very difficult to inflate. Such a problem, called respiratory distress syndrome, occurs in premature infants, okay, and can be fatal. Normally, a substance called a surfactant reduces the surface tension of the mucous lining of the alveoli, so they can be inflated properly. Some infants lack surfactants and only can breathe with very great effort. So when they don't have that surfactants, then they have to be on a breathing machine which is pushing air. Okay. So what is happening in their case is the following. So this is the normal surface tension. This is the normal pressure inside the alveoli. In their case, the surface tension is higher. There's the normal pressure. Okay. So let's say if the excess pressure is higher, what happens? So if that pressure is 11 millimeters of mercury. Okay, now if this newborn baby is trying to breathe, to breathe, you lower your diaphragm, and the pressure goes down to -8 millimeters. Okay, 11 minus 8, that's still +3. You can't have air coming in. That's still higher than atmospheric pressure. You have trouble inflating your alveoli. So the only thing to do is you have to pump air at higher pressure. Okay, so they have to have breathing machines. Okay. So okay, so the surfactants in your on the alveoli surface reduce the surface tension to that. Okay. So that's how breathing happens. Okay, again, we talked a lot. So here's the punchline. To breathe in and out, what you're doing is the following. The atmospheric pressure is constant. What you're changing is the pressure inside the alveoli. When you want to breathe in, the pressure here is to be lower than atmospheric pressure, so air can move in. When you want to breathe out, this pressure has to be higher so that air will move out. Yeah. You guys have heard of collapsed lungs? Okay, what is that? What is that? So, see, I said there's partial vacuum in your thoracic cavity. So let's say you get in a wreck or something and that thoracic cavity gets punctured. Now the pressure is 0 millimeters of mercury. And this pressure is higher and all the air will go out and this balloon will collapse. Okay, that's a collapsed lung. Okay, so if you destroy this partial vacuum, then your lungs will collapse. Mm-hmm. I'm sorry?
Sometimes the option is having a chest tube.
What is a chest tube?
So that it's like a replacement to help you with the...
So vacuum, yeah. So you're sucking air out of there and creating vacuum. Yeah. Till that thoracic cavity is repaired. Yeah. Okay. So again, I hope you guys understood that. So that's the breathing mechanism. Okay. So you have various problems with the issue. Again, the point of all that was the importance of this formula is, so if you have some kind of disease and this thing is too high, then you have a problem. Okay, then you have trouble breathing in. If this gets too large in an emphysema patient, then the pressure is too low and you have trouble breathing out. Okay, when this is too large, you have trouble breathing in. When this is too large, you have trouble breathing out. Okay, so that's the problem. And okay. All right, now we'll talk about a different phenomenon. Okay. So ultimately what we want to address is the following. So the redwood trees are quite tall. Some redwood trees can be taller than 2 football field lengths. Okay, and the question is, how does water get from the roots to the leaves? Okay, so that's the question we want to address. Okay, so before I go into the details, so here's you guys all know capillaries. Capillaries are thin tubes, generally made of glass. So here's a capillary. See, here's a wider capillary. You put it in a glass of water and water rises. Thinner the tube, higher the water rises. Okay. You do the same thing in mercury, instead water depresses. Again, thinner the tube, the greater the depression. Okay, so we want to understand what is going on here. And is this how trees raise water up to the leaves? Okay, so that's sort of the question. All right. Did you guys understand where we're going? Okay. So we'll talk about adhesive and cohesive forces. Okay. So So if you have a glass of water, adhesive forces are the forces between the molecules of water, and cohesive forces are the forces between glass and water. So those are, oh no, cohesive forces are forces between like molecules, and adhesive forces are forces between unlike molecules. So cohesive forces are forces between like molecules, and adhesive forces are forces between unlike molecules. Okay, so in this case, it would be glass and water and glass. This would be adhesive force. Cohesive forces would be water and water. Okay, so this happens when the cohesive forces are greater than adhesive forces. So the forces between mercury molecules are greater than forces between mercury and glass. And this happens when adhesive forces are greater than cohesive forces. Okay? Adhesive forces are forces between water and glass is greater than forces between water and water. Okay? All right. So adhesive force, okay. Adhesive forces vary in strength depending on the material involved. Water adheres well to glass and rather poorly to wax. Okay. Strength of adhesive forces has visible effects on how a liquid wets a surface. So what this is, so let's say this is water on glass. This is the same water on the same glass surface, except that glass was waxed. Okay, so here, when the glass surface was waxed, okay, this is waxed. Okay, water spreads out on many surfaces because adhesive forces between water and the surface are larger than the cohesive forces. So when this happens, the adhesive forces are larger than cohesive forces and it spreads out. When this happens, the cohesive forces are larger than adhesive forces, and it forms bubbles, okay, or it forms droplets. Okay, so this is adhesive forces are greater than cohesive forces, and this is cohesive forces are greater than adhesive forces. Okay. All right, so for a liquid to wet a surface, the adhesive forces must be greater than cohesive forces. And when the cohesive forces are greater than adhesive forces, it doesn't wet a surface. Okay. All right, so high surface tension in a liquid, so surface tension is that gamma. So high surface tension in a liquid tends to inhibit the wetting process. High surface tension means high cohesive forces. Okay? So larger the cohesive forces, larger the surface tension. And so inhibits the wetting process. Yeah. Water has a relatively large surface tension and does not easily wet many substances, such as polyester fabric. So when you put soap in water, what you're doing is you're reducing the surface tension, and then it wets polyester. Okay. Soap, a surfactant, reduces the surface tension of water, allowing it to penetrate and wash away particles of dirt much more effectively than plain water. Okay, so surfactant, when you put a surfactant in a liquid, you're reducing gamma, the surface tension. There you go. So capillary action is the rise or fall of liquid in a tube owing to the interplay of cohesion of a liquid to itself and adhesion to the wall. Okay, so this is because cohesion and adhesion, it's a comparative relationship to that. Okay, when adhesive forces are greater than cohesive forces, the fluid will rise. When cohesive forces are greater than adhesive forces, the liquid will fall. And so for water, when the adhesive forces are greater than cohesive forces, you have a meniscus forming like this, and this meniscus will raise the water, will pull up the water. When cohesive forces are greater than adhesive forces, the meniscus will be like that, and that's pulling the water, pulling the fluid down. Okay, so this is for mercury, this is for water. And so mercury is depressed in this fluid, and water rises in this capillary. Okay, and you can see that narrower the capillary, more the fluid will rise. Okay, and we want to know how high it will rise, and this formula tells you this. Okay, the height to which this fluid will rise is proportional to the surface tension. Greater the surface tension, greater it will rise. It depends on the density of the fluid and the radius of the tube. Smaller the radius, higher the water will rise, fluid will rise. Okay, and that you can see that here. All right. So you see capillary action. Okay, and now we'll talk about how water rises in plants. Okay. Okay, the question of how tall trees raise sap to their uppermost branches is a controversial one. So it's not well understood, it's not generally accepted yet. Veins in trees are not small enough to raise the sap more than 10 meters. So what they're saying is these tubes are not narrow enough to raise the water to more than 10 meters. 10 meters is twice the height of this room. You've seen trees taller than that. Okay? So how does water get to the top? Okay, osmosis produces root pressure. We'll learn about this next chapter. Root pressure, which can also be shown to be inadequate to force sap. So there's an osmotic pressure that'll raise it up a little higher, but that doesn't explain how water gets to the top of tall trees. Okay. It has been suggested that cohesive forces pull sap along in a long chain. Okay, so what cohesive forces are, so imagine a long chain of water molecules. Okay, so this water molecule in the leaves, it evaporates, and when it evaporates, it's pulling these water, the next molecule which is pulling that, so think of them as connected as rings of a chain, and when this ring goes away, it's pulling the other chain. Okay, that's another explanation. Okay. So, especially when impurities. Okay. It has not been possible to recreate sap behavior under laboratory conditions. Okay. In a lab, we haven't been able to raise water up to those heights that redwood trees raise the water. Okay. Our condition, or to understand the phenomenon theoretically, we don't really understand it. So the question remains open and under active discussion. All right. So we learned about capillary effect. We'll learn about osmotic pressure that'll raise water up, and we learned about cohesive forces. Okay. All those three still don't explain the water rising up. Okay. All right, so that ends chapter 6. Okay, what I'm going to do is